Welcome to section 2.3, the relative positions of lines and planes in three-dimensional space. So now that we know a little bit about the equations of lines and planes in R3, how to describe them algebraically, we are going to look on the geometric side and determine the relative positions between lines and planes in 3D space given their equations. And we are going to use mostly vector methods to determine the relative position of different lines and planes. But it should be noted that one can also talk about the number of solutions in the intersection of these objects to arrive at the same conclusions. So let's go ahead and look at section 2.3.1, the relative position of two lines. Now we are going to, in subsequent videos, look at a line and a plane and two planes, but for now let's just focus on two lines. And what you see on your screen at the moment are three cases that are probably familiar to you from high school or from your calculus class. And they are three positions that two lines can hold relative to each other. So first of all, we have two lines can be parallel distinct, or just parallel is what we tend to say in this case. And parallel lines, of course, as you know, are lines that never intersect. Two lines can be parallel coincident, or we will just say coincident. And those lines are lines that actually occupy exactly the same set of points. So they intersect at all their points. And the third case that I expect that you are familiar with is that when two lines are intersecting at a single point, and we will just call those intersecting lines for lines intersecting at a single point. Now these three cases exist in R2 in two-dimensional space. They are also possible in R3, but in R3 there is a fourth possibility. There's a fourth case that I expect you are not as familiar with, and that is a case actually that we talked about a little bit in a previous video when we talked about lines in R3 not needing to have intercepts at all. They can miss the axes entirely. And so that fourth possibility here is when lines are skew. And that is what we will call them. They are skew. And skew lines are defined to be non-parallel, non-intersecting lines. So you can imagine like a road going under a railway bridge or something, right? If a car passes underneath the railway, it's not going to get hit by a train should there be a train at the same time. These lines are lines that would be intersecting if they laid flat together, but it's like we put some vertical distance. We've got to be careful with what we mean by vertical, but we put some distance between them. So those lines are skew. And now we know from the equations of lines that we can determine from their algebraic equations the objects that we see here. We can determine direction vectors for each line, and we can see points on each line. And so we're going to use these vectors and points to be able to distinguish the cases that the lines are in based entirely on their equations. So the first thing that we are going to look at is the direction vectors, d1 and d2. Right? And so the first thing in each case that we will examine is the direction vector of the first line parallel to the direction vector of the second line? Right? So they don't need to be the same, right? They just need to be multiples of each other to be parallel. And so you look at parallel, well, it's in the name, parallel lines will have parallel direction vectors. Coincident lines will have parallel direction vectors. Intersecting lines, well, if we took a look at the direction vectors there, they are not parallel. So for intersecting lines, the direction vectors of the two lines will not be parallel, and incidentally, that is also the case for skew lines. So right away, we're able to, by simply examining the direction vectors, we are able to break up the lines into two sets of cases. If the direction vectors are not parallel, the lines are intersecting or skew. If the direction vectors are parallel, well then the lines are parallel or coincident. So we need to go a little bit further. We need to dig a little deeper to be able to distinguish between each of the pairs of cases. And the way we're going to do that is by joining the 2 points. So if we join P1 to P2 and we create a vector P1, P2 in each case, well, that is going to be enough here to help me distinguish between parallel and coincident cases. So if we look here, P1, P2 in the parallel case, P1, P2 is not parallel to the other two vectors. Right? So if I note that down, P1, P2 is not parallel to D1, which is parallel to D2. But in the coincident case, all three vectors are going to be parallel. So P1, P2 will be parallel to D1, and that also makes it parallel to D2. So taking these two sets of criteria together, or these two criteria together, is going to help us determine exactly when lines are parallel. They have parallel direction vectors, but the vector between any 2 points on the line will not be parallel to those direction vectors, whereas the coincident lines will have all vectors parallel to each other. So what is left then is to distinguish between intersecting and skew lines. So both of these, we have said already, have direction vectors that are non-parallel. We are going to use the idea of distance between the lines. And again, if we connect those two vectors, those 2 points, to create our vector P1, P2, we should notice something that will feel familiar from our chapter on vectors, and that is here that all the vectors lie flat. And if they all lie flat together, we call them coplanar. All the vectors are coplanar. And here the vectors do not lie flat. Vectors do not lie flat. And when vectors do not lie flat together, we call them non-coplanar. And you had a wonderful test in your chapter on vectors for coplanar and coplanar. This is very difficult for me. Coplanar and non-coplanar vectors. You had a very lovely vector test for that, the triple scalar product. So if we take P1, P2 dotted with D1 cross D2, if the vectors are coplanar, the triple scalar product should give us 0. And if the vectors are non-coplanar, P1, P2 dotted with D1 crossed D2 should be non-zero. So there is the extra criterion that we need to distinguish between intersecting lines and skew lines. So let's just review. Intersecting lines will have non-parallel direction vectors, but coplanar vectors P1, P2 with D1 and D2. The triple scalar product will be 0. Skew lines will have non-parallel direction vectors and non-coplanar vectors P1, P2, D1, and D2. So the triple scalar product of those vectors will be non-zero. So there is a set of vector methods to help us distinguish between parallel, coincident, intersecting, and skew lines. In the next video, we'll do an example to practice this with some actual lines given their actual algebraic equations, and then we will do a little summary and come up with sort of a flow chart to capture all of this information succinctly in another form.